Okay, I think it's time to start. Oh, I probably should put this to Reddit first. Okay. Oh, code, that's the one. Okay. How do I submit? Submit link. All right, it's starting. Okay. Hi. Welcome back. I've not streamed for quite some time now, and a lot of this is due to a lot of this is due to changing houses, lockdowns, that sort of things, and it's been quite a long time. But I would like to get back into the habit of live streaming my code or even my thought processes. So I thought, why not do something about Gorgonia, which is something that I can actually keep up with, as opposed to new projects like LSP or Game of Life, which while interesting, it didn't really keep my interest. Okay, it did keep my interest, but not. My interest has sort of moved in a different direction from what I had originally planned. I may come back to that, but right now let's focus on Gorgonia, because I seem to be very easily distracted, right? And yeah, so I guess Gorgonia is one of the projects which I can stay undistracted, because it's one of those things that I keep coming back to. So today what I want to do is basically write a differentiable if then else. Now, if you do not know what Gorgonia is basically like TensorFlow and like PyTorch, but it's written in Go, and it's actually written before TensorFlow or PyTorch even came out. It was written back in the days of Theano, if you know what Theano is. So Gorgonia basically does what TensorFlow does. It does what PyTorch does. It does symbolic differentiation, and it does automatic differentiation as well. So when it comes to these things, I treated Gorgonia as a new programming language, right? When I designed Gorgonia, it is treated like a new programming language. And one of the things that is missing from Gorgonia is if then else. Now, very recently, I wrote something called min between and max between. It's an operation that takes two tensors and does an element-wise, find the min or max between. And it turns out that min and max is actually differentiable, right? And the differentiation is the differentiation is quite simple. Let me show you. Switch to the coding window, and this is the differentiation algorithm. You first check if it's equal to the output, and then you you call it the mask. So you take A, and then you check whether it's equals to the output, and then make it return the same type. So if it's a float 64, if it's tensor float 64 tensor, A is a float 64 tensor, out is a float 64 tensor, and when you compare them, you return 1 or 0 for the mask. And then with that, you can actually just element-wise multiply, and then do your subtraction, and you've basically got a gradient that you can get. And that led me to think about how I would be. Well, I've actually known how to implement this for some time now. For example, abs is also abs is also differentiable. So I've just not got around to implementing it. So yeah, right. So I just like to implement if then else that is differentiable, I guess. Yeah. So let's get started. But first, let me just get to explaining a bit. Okay. So the trick to figuring out how to differentiate these things is how to differentiate an operation is getting an operator like equality, but returning or doing the operation in such a way that it returns the same data type, right? So with equality, well, it's not showing up. Okay, with equality, we can say the type is any type and any type and returns a bool, right? So we can say if A is type of float 64 and then B is float 64, well, bool is going to return a bool, right? Okay, so we can say 1.0 equals to 1.0 because this is a float, and the result would be a true, which is a bool. Yes? Okay, the trick is to turn this into the same type as this. Okay, and so let me show you an example, and let's take a very simple example, the Colettes conjecture. It's a very fun example, but the Colettes conjecture is basically this, right? Colettes. All right. Now we can simply write this Colettes conjecture as 3x plus 1. If odd, we can just change it, right, to x. Okay, and then when you've got multiple cases, it becomes an OR, and OR is just simply a plus. Okay, so now here I introduced this operator, the percent sign, and this is actually a remainder operation, right? So for we know this, right? Okay, and on that note, the equality sign is it evaluates to 1 when it's true, and evaluates to any number that's not 1 when it's false. Does that make sense? So not 0 implies true. Following so far? So the Colettes conjecture, if we continue with the Colettes conjecture, we can say something like this: Colettes 5 equals to, okay, is it showing up on my screen? Yes, it is. Okay, good. Well, 3 times 5 plus 1, and then times 5 remainder of 2, not 0, plus 5 divided by 2, equals 0. Now, if we evaluate this by parts, this part would be, so this part would be 16, and this part would be 1, right? This part is 1, plus 2.5, and this part is, I'm using floats for now, but imagine you can, I guess you can imagine non-floats. But this one would be 0. So this part would be 0. And thus, the answer is 16. Yep, the answer is 16. So the Colettes of 5 is 16. Pretty simple. So this will always get evaluated, right? Both branches, the left branch and the right branch will always be evaluated. And because they will both always be evaluated and then the results added together, this makes it differentiable. Now, the Colettes conjecture itself it's quite interesting, right? So I think it's quite simple to see that all even numbers will eventually reduce to 4 to 1. The Colettes conjecture is whether there is any number that will, is there any x in the Colettes of x that will not yield a 4 to 1 loop, right? So if you take 16, for example, from here, 16, and you go the next number, if you apply Colettes recursively of 16 equals to, well, the answer is 8, which is then 4, which is then 2, which is then 1. And we choose to stop at 1 because, well, it's a loop. 1 will lead back to 4, and so on and so forth. Yeah, right. Yeah, 1 will lead back to 4, and then you reduce back down to 1 again. So that's essentially the Colettes conjecture, whether there is any number x that will not lead to this 4 to 1 reduction when the Colettes function is recursively applied to the value, to all values. So we can quite easily see that all even numbers sort of goes to 1, right? But what about odd numbers, right? So, well, odd numbers will always go into an even number. So let's say, let's show a very simple proof, right? So if it's an odd number, we choose the first branch, 3x plus 1 if odd, right? So let's only consider this branch of the if statement. And so if x is an odd number, so x would have a form of 2n plus 1. So times 3 plus 1, well, that's equals to, what's it? 6n plus 3 plus 1 equals to 6n plus 4. Well, we can now factor 2 out. That becomes 2 to 3 n plus 2. And we know that this form 2m is a even number. Well, if even this is an even number, right? So the lemma is very simple. It says that all odd numbers will eventually become even numbers, and yeah, Then hang on. Then all even numbers will then become 1. That doesn't sound right. Okay, I think there is I think there's something wrong with that lemma. So the idea that all even numbers will eventually become 1 is wrong. Okay. Yeah. What is a general? Okay, so 2m is an even number, and okay, well, this is interesting now. I take that back. I take my previous statement back that all even numbers eventually becomes 1. That's not correct. So let's see if that's correct. So if x over 2, if x is even, this is the other branch, right? So we evaluated for all odd numbers, we know that it will eventually become an even number. So let's look at for all even numbers. So let x be a number of 2n form. Okay? And so okay, so this is a problem, right? If you do x equals to 2n, then if you evaluate this branch, it becomes n. So n of x over 2 equals to n. And here we are stuck because we do not know what n is. So here's another question, right? N can be even or odd, and then you go back to the case again. So I'm wondering if there's a general form. So n could be even or odd, and now we will not know what the result is unless we actually apply the Colettes conjecture again, Colettes function again. Right. Is there a more general form of numbers? Let's see. So odd numbers is in this form. Is even numbers is of this form. Now, if we can combine these two, and then we can have a more general idea of numbers. Here to here. Okay. Actually, there is. I think there is. Okay. I think there is. You can take any even number, right? And then multiply a 2 in front, and that makes an... Sorry, you can take any odd number and put a 2 in front of it, multiply by 2, and then that makes an even number. And then if you multiply by 2 again, that makes another even number. So you're basically constructing even numbers right now. Oh, yeah, 2 to the m, 2 to the 1, 2n plus 1, and this is a more general form of an even number. So if x equals to 2 to the m, 2n plus 1, then x divided by 2 is equals to 2m minus 1, 2n plus 1. Okay. So if you reduce m times, you get an odd number. Right. Okay, let's see if this intuition is even correct. Okay, so even numbers have this form. 2 to the m, 2n plus 1. Okay, so let's try what the base case is. So if m equals to 0, then 2 to the m becomes 1. So if m equals 0, any number that happens after that is an odd number. If m equals 0, any implies odd number. Okay. So the base case cannot be m equals to 0. The base case must be m equals to 1 at least. and say n equals to 0. So that will be 2 to the 1 times 0 plus 1 equals to, well, 2. Okay. So we have a way to construct numbers now. That's interesting. So if we have a way to construct numbers now, then we can construct numbers. And we can look at it. We can find out how the numbers look like. So, okay, right. N equals to 0, M equals to 0. Make a table here. Okay, go to the next page. N and M, 0, 0. The resulting numbers would be 1. Right? N equals to 0, M equals to 1. The resulting numbers is 2. Okay? N equals to 1. Oops, what's this? N equals to 1. And M equals to 0. Result would be 2 to the 0 plus 2 plus 1 equals to 3. And so N equals to 1 and 1 equals to 2 to the 1. 2 plus 1 equals to 6. Okay. Now, this is starting to look a bit interesting. N equals to 1, M equals to 2. Let's do this a bit more, right? So 2 to the 2 is 4, and 2 plus 1 equals to 12. Okay. So we can now construct, I think we can construct all the natural numbers from a tuple of numbers. So let's say a tuple of 0, 0 equals to 1, and a tuple of 0, 1 equals to 2, and so on and so forth. Okay. Now that's interesting. Okay. So if you start out here, 0, 0, and then you branch out. So it's a binary tree, I guess. Here would be 1, 0, and this one would be 0, 1. This would be equals to 1. This one would be equals to 2, and this one would be equals to 3. Right? And then from this, you branch out to another binary tree. Yeah. On the left side, you add 1 on the left, so 2, 1, 2, 0, and here would be 1, 1. Here would be 0, 2 equals to 4, and 1, 1 equals to 6, and 2, 0 equals to 2, 2, 0, 0 plus 2 plus 1 equals to 5, and equals to 5. So 1, 2, 3, 4, 5, 6. So you can keep going like this, and it's not a binary tree, it's a graph. It's a grid. Okay, so these are coordinate systems. If you just flip them around, if you take this and then this, you basically have a grid system that looks like this, where 0, 0 is here equals to 1. And so what is 0? Okay, well, 0 is unique, right? So it would be like this, 0. It's a very weird number table. It's a weird... You no longer have a number line, you have a number plane of sorts, but this is not... so your natural numbers can be replaced by a plane. And that's interesting. Okay, I think I've just spent the last 30 minutes talking about this without actually writing anything. So maybe we should write some code. You know what? Let me just tweet this. This thing has now turned into a Colettes thing. So I got sidetracked again. I'm sorry. I'm just going to change this title into Ruminations of the Colettes conjecture, I guess. Maybe not. Another way to think about natural numbers. Yeah, why not? Okay, now I've just changed the video title. I'm just going to update this with a tweet. Turns out what less of what I planned and more rumination on different possible representations of natural numbers, because yeah. Okay, let's get to actual coding, because I think I've spent quite a lot of time. 30 minutes is yeah. Yeah. Let's do that, shall we? Okay. You see? Okay. This is the min max thing that I was doing. But let's not do that now. Let's not. I'm just going to ignore that now. Yeah, sure. Why not? So yeah, Colettes or nets main.go. H main, bank main. All right. So right. Let's open up a shell. Okay, we have this, and what do we want to do? Right. So what we want to do is we want to represent the natural numbers. Okay, so very simple. Oops. And an M, and we'll just go with uint because, right? Okay, so that's the definition of a natural number, and let's write a format for it. Okay. So putting this makes the net data structure actually implement thumb.formatter, and let's say right, so okay, so I'm going to also create a function called HR, which HR means human readable. And basically converts this back into uint, right? So there is no power 2 in uint. So we'll have to write power 2 ourselves. Yep. And times 2 times n plus 1. So this part is the odd number, and this part is the generalization of an even number. Okay. Now, oops. Right. So we have this now. Func pow, which is what we have to write. So 2 to the power of something, right? That's the definition of pow, I believe. Okay. You know what? Let's try this. Let's n equals to net 0 0 fmt.print f. Oh no, just print f n. That's correct. Go run start.go. Yeah. Okay. So if n is 1, yeah, okay. Let's look at this. N is 1, m is 0, that's 3. That goes very well according to there you go. N is 1 and m is 0. That's 3. Okay. So this is fairly simple. Let's go back to the coding window entirely. Yeah. Okay. But you know what? I'll also add an option to actually print. I'll add an option to also sort of print so you can see the structure of this. So if there's a hash flag, I guess, which is the common thing in Go, to is like if you want to print extended things, you just put a hash flag in there. And so we just return the print. Okay, so this is the number n.m return. So let's try this. Yeah. Okay, so now we've got 2 ways of doing this. Okay, that's pretty nice. Now we need a way to convert a natural number, as in 1, 2, 3, into this net structure. And I'm freaking lazy. Okay. So what am I going to do? I'm going to drink some water. Okay, what is the main goal here? The main goal here, I think, is to explore the Colettes conjecture to explore the numbers of a Colettes sequence, right? In the presence of this, and I think I've got some good ideas. I want to plot this data structure out. That grid that I drew earlier, I think we can turn it around and start plotting. Yeah. Okay. Okay, so Let me check the YouTubes. Everything is still going right. Okay. Yeah. I just dropped all my users. Okay, I got my users back. Not bad. All right. So, okay, what we'll need is a grid, I guess. Oh, okay. Convert from a known integer into this net, and because I'm very lazy and the main goal is to explore the Colettes sequence, so I'm just going to be lazy and just do this. Okay, so what I'm going to do is I'm going to initialize this program with a list of already known integer and net pairs, right? So I'm just going to create a list of nets here, and the index of this list would be, so if it's 0, it's 0, and yeah. Okay, that makes sense. Now we just need to write an init function. You know what? Let's just move this away. Okay, so net.go, and we move this here. Move this here. All right, everything should work fine. Right, so we'll write an init function to initially populate this known thing. And yeah, so we're gonna we're gonna start with it. We're gonna start iterating m and n, and because m increases 2 to the power of something, so we don't have to increase m as quickly as n. So for n in uint of 0 and n is less than, say, 10,000, I guess, n plus plus, and for m uint of 0, but you recall that when m goes up, it's times 2, so it's 2, 4, 8, 16. Okay, so we just go up to 16, I guess. Okay, and then now we just append all the known ones. So this is, oh, okay, now we will have to sort this, and we can quite easily sort this. Yes, okay, good. We can easily sort this by using the HR function, HR method. Known func ij known I dot hr is less than known j dot hr. Let's see if sort's included. Yes, sort's been updated, and now we can have an int to net function. Yeah, but this will only work for the first, well, n times m that, right? Yes. So this is a very, very simple and a cheating method, I guess. Yep, that's the one. because we minus 1 because this index 0 would be number 1. Index 1 is number 2. Index 3 is number 3, and so on and so forth. Because there's no representation of 0 in this form. There is no way we can represent 0 with this net data structure, because 0, 0 is just 1, right? So there's no way to represent 0. There's in this universe, there is no 0. There is, your numbers start with 1. Your natural numbers start with 1. And if n.hr is not equals to a, then we know there's a problem. Panic. Shit. Otherwise, we return n. This will panic. Right. Maybe we want to print the length of known as well. To see how many numbers we actually generated. Okay, length of known is 16. Oh, of course, yes. Of course, it's 16,000. This times this, you know, is 2 loops, n times m. Yep, okay, never mind. Being a dumbass. Right, so if it's smaller than 16,000 numbers, then I guess it's not going to be found. Yeah, and I'm guessing that there will be some gaps. We'll worry about that when it comes to it, I think. Okay, now let's think about the next thing we want to do. Okay, we want to actually explore the Colettes conjecture, right? So why don't we write the so this is the box standard Colettes, right? If a simple. Yeah, there's no need to test this because I'm very sure it works. And we also want to have a function that recursively apply this. And we'll instead of returning the last value, we'll just return the sequence that it goes along. So yeah, and we stop when a is 1 because 1 will go to 4, will go to 1, go to 4, and so on and so forth, right? So does this make sense? Okay, so we've already done something that we know of. So let's just delete all this. We know that it works. Why Colettes of 5? We should have 16, 8, 4, 2, 1. 15, 5, 16, 8, 4, 2. Oh, right. Yeah, okay. Okay, you need to actually append 1. Yep, 5, 16, 8, 4, 2, 1. And we can see the weird one. I think it's 13 is the weird one that goes to hundreds in the numbers. What was it? 7 was a weird one. That it goes into a very, very long sequence. 7, 22, and one of them goes up to the thousands, and in the early numbers, I think 13 or something. Well, anyways, that's not my point. Yeah. Is anyone? Okay, let's see if that makes sense. Yes. Okay. Good. Right. Now, Okay, now the next thing we want to do is actually the plot. But we need a now we've got a list of a sequence. Now we want to convert this sequence into a sequence of nets. That is fairly simple. Yep. Right. That is very simple. How am I going to do this? Internet. We've got internet, yes. Okay. No. Ints to nets. There you go. Is it internet? Internet, small n. You know what? This should not be small n. This should be big N. Okay, now let's plot this with yes. Let's plot this with Gonam's plot, shall we? So how do I start? You know, I almost always refer to my own book, not a plug, but I actually do refer to my own book on how to start plotting stuff. It takes a while, but I do generally remember after a bit. Again, I'm not trying to plug my book. If you want to get my book, you can just come ask me for it, because you know I don't really make a lot of money from it. Right, I actually bookmarked this. It's around page 108. Yep. Okay. Not page 108. Page 100. Okay. P plot dot new. So this differs from my book, because in my book it was using the old version of Gonam, and the old version of Gonam actually returns an error if you use the old version of Gonam. But if you use the new version of newer versions of Gonam, you will not need this. I think why is this not importing? Okay, P is plot.new. Am I using the old version? Yeah, maybe. Nope. Okay, I don't know what version of Gonam I have. Okay. Right. There's a plotters. 1 second, I'm going to go doc. Sorry. I don't remember. Browser? There you go. Browse web ewww kg.go.dev /gonam/v1/plot. Nope, not found. EW. Okay, that's the one. Capital G. Yes. kg.go.dev /gonam.org /v1/plot. Please work. Yes. Excellent. Okay. Plot. Right. Plot.new. Yep. Plot.new returns a new plot, and I think it's plot.plotters. Yeah. /plotters. Plot. Nope, it's not plotters because, you know, plotter. Yep, correct. Plotter's the one, and what I want is a line plot. New line. XYs. Okay, I know what XYs are. XYs are basically nets, more or less. Yeah. So, so here's plot.new. It's not importing. I'll manually import it later. And line, it's plot.new. Don't care about all those. Plotter.new line. And it returns an error, which, because I'm a badass, I'm going to ignore. Actually, even I didn't. Something here, I guess. Okay. Func ints to xy's. Or maybe not. No, let's try this. Func nets to xy's. There you go. And we'll return a list of xy's. That will be plotter.xy's. Does this make sense? Yes, it does. So here we'll have to nets to xy's of y Colettes of 13, for example. Now let's try the crazy one, 7. Right, 7 is the one that goes long. Okay. Yeah, so this my eglot's not working, so as usual we'll have to do this. Brilliant. Now this needs to be filled in. Right. So plotters.xy, let's look at the def right. And xy is a struct, right? Yes, xy is a float 64. Okay. So which is it? Nets.go would be n and m, right? Okay, good. We'll make xn and then ym. So y is going to exponentially increase in size, and this would be linear. This would be exponential. All right, makes sense. Of course, it makes sense. Yes. That makes more sense, I guess. Yep. Okay. What's this? And declared but not used. You must be joking. Okay. Yeah, this is the problem with LSPs. They generally don't work very well. So yeah. So after this, we need to add the line plots to the plot, right? P dot. Sorry, let me look at the book again. P dot add. Yeah. Line. What is this? Okay. Anyways, this is a bit of a joke, right? DIE is die if error. DIE is DIE if error. That's all. It's a bit of a joke. Right. And then we will save this with 100 by 100 pixels, and we'll call it colettes.png. Let's run this and see if it works. Yep, okay. Go get dot. Right, go mod init, because, you know. Yeah. Okay, that's why it was not working. Because I forgot this is a brand new project. We have with no GoNum and with no Go mod, and it's anyway. Right. Okay. Yeah. Nets to xy. Okay, we'll have to ins to nets. Okay, now let's look at the files. Is there a colettes.png? Yes, there is. And guess what? 100 by 100 pixels is very small. Let's look at this on the video screen to see how big it is. Yeah, it's very small. So let's make this 500 by 500, I guess. Okay. So here we see it starts off at what's 7? Okay. Instead of doing this, print F. Eh? Oh, right. Yes. No. What I meant to do was ins to nets of this. Y colettes. There you go. Here is a list of 30. This would be 7. And then it goes to 22. Then it goes to 11. 50. Yep. And then 50 is 11. This is 50. 81. 80. 62. 61. 61. Oh. 62, 61. Okay, so there are 3 stops here. Maybe I should put them tick marks, I guess. And then it goes to 23, and then 2221, and then it goes to 04, 03, 02, 01, 00. Okay. So it sort of wraps around, I think. Imagine there's a geometry that represents this. Probably too much to implement tonight. It's already 10:30 at night, and I have been streaming for 1 hour. So imagine if this. Okay, let's try something else. Not Colettes of 7. Let's try a long Colette sequence. Let me Google what's a long Colette sequence. All right. I don't want the longest Colette sequence. Yeah. Okay. I don't care. Good for you. 949 steps. That's too much. And this is a very huge number, which I don't think... Okay, let's say you want a long sequence. Okay, instead of doing a long sequence, let's do a short sequence. So short sequences would be going to the right and stopping. Nope, it always has to come back to 0, so it has to go to the right and then come back. All right. Is my intuitions correct? Let's... No freaking clue. Ooh, what happened? All right. So, let's look at the card. So it goes from... It goes from... 13. Okay, this is 13. And, oh, right. Yes. This needs to... Okay, it goes from 6, 0, and then all the way down. So if it's a short sequence, it goes from right to left. But then there will be sometimes where it goes from right to left. Okay. Nope. Let's just try something like 301. Is this a long sequence? Longer, but it goes like this. It goes from right to left. There's no particular pattern. I was wrong. So I had originally thought that might be a geometric. So I don't know, something, right, that makes it seem like it's wrapping around and going back. Like if you wrap this graph in a cylinder and then sort of flatten it, you get that. But I don't think that's the correct way of thinking about it. Let's try 303. Aha! Here's a very long one. Jesus, what the hell is this? Okay, it goes See, with a very long one, it goes right, up, down, up, down, and then it goes, and then it sort of wraps around and goes to the left. And then what is, okay, I think the x-axis needs to be a bit longer. Height times width, width times height, I think. Okay, this is a bit weird looking. Huh. Wow. I definitely did not expect something like this. Okay, so there's a motion towards the right, and then there's a motion towards the left, and then something that happens here, which is... I wonder if you can make a grid. So, right, Mike tells me 27 has a long Colette sequence, so let's do 27. Because, thank you, Mike. It's, oh, that's very long and very beautiful. Oh, wow, what's this? Okay, it's more squeezed towards this end. And then you've got this weird, super long arcs. Or you got this bit where it goes right, and then goes left, and then goes right again. Okay, I like 27. Thank you. That's... oh. Okay. Right. Maybe it's got to do with the gradients. No, the gradients change. Maybe we can take the map off the gradients. So for each sequence, you calculate the diff. And then plot the gradients. What the hell? You know what? This is very interesting. Very interesting, and I would really like to continue. I'm just going to die. Sorry, I'm thinking this is not what I had expected. Then again, there is a reason why the Colettes conjecture is not solved, right? So I expected some nice patterns, I just did not expect this kinds of patterns. Yeah, okay, look, it's 10:45 at night, and it's pretty late, and yeah, I think I should go to sleep. I still have a few pull requests to actually finish. So, all right, thank you so much. I think it's been a pleasure, and it's been pretty relaxing for me to code. And thank you for joining me. Thank you, Mike, for suggesting 27. I may work on something on this maybe in the future. I might as well put this up on GitHub or something. I'll put this up on GitHub. It'll be called Colettes or something like that. Yeah. Okay. Thank you so much. Thanks for joining me. And right. Bye, I guess.